Newton's Second Law of Motion and Momentum by Stephen Kennedy. The materials you'll need are a mouse ball, a 1-inch notebook, a plastic tube with a diameter larger than the mouse ball, a meter stick, a balance, a camera, and a tripod. With the items arranged on the table as you see, we're ready to begin. I'd like to start this lab off by first introducing a few terms.
Newton's second law of motion, which means that acceleration is proportional to the net force, or that the net force is proportional to the acceleration. Force is the capacity to do work. Force is a vector, meaning that it has a magnitude and direction and is used to quantify the interactions between two bodies. Force can be simply defined as a push or a pull. Mass is the amount of matter in an object. It is often confused with weight. Mass is the same wherever you are, on the moon, on the earth, or floating in space. Your weight depends on gravity. Acceleration is a vector, meaning that it has magnitude and direction, a quality that describes the rate an object changes its position. Acceleration is often confused with speed. Speed is only the rate of change. The momentum principle adds to Newton's second law of motion. It extends the meaning by introducing the concept of a system. A system looks at both internal and external interactions and predicts how the system will react. Delta P is symbol used to describe the change in momentum. Delta T is used to describe the length of interaction. This time affects the change of momentum. This is known as impulse. Newton's second law of motion.
As you can see, by utilizing a free body diagram, you can identify the major forces that have acted upon the mouse ball. These forces are part of a system that consists of both internal and external forces. The net force, or instantaneous sum of all vector forces on the system by the surroundings, are called the external forces. An internal force to the system may influence another internal force in the system, but the internal forces cannot change the momentum of the system. There are three forces acting on the ball: the frictional force, the weight, and the normal force of the surface on the object. This is as though there were a push upward on the table and a pull downward on the ball. Clearly the weight and the normal force cancel, so that the net force in the vertical direction is zero. The momentum principle, or Newton's second law, also states that an unbalanced force acting upon the ball causes the ball to accelerate in the direction of the force. You can observe this as the force of gravity causes the ball to roll down the incline. With the tracker program, I have utilized a meter stick in the video and the calibration stick to set the scale for the system. After placing the origin several frames from the ramp, I began to set data points as the ball rolled in the x-positive direction across the table. Utilizing my observation, the initial start time and the ball's x position, along with the second time and x position collected from the t-chart, I will apply the average velocity formula and estimate the average velocity. Be sure to use the Nix value in the chart, as the results will be more accurate. With the data collected, I modified the vidle Python file to represent my system. I entered the ball's mass, the initial position, the initial start time, and the calculated velocity from the previous step. Delta T should be 100 times smaller than the motion recorded on your original video. I modified the while t loop by inserting my final time value. Also, I inserted Newton's second law into the ball vel and ball pos assignment statement as shown. And by editing the fnet vector line to 0, 0, 0, our prediction will have constant velocity. My computer model is similar to the mouse ball that I videotaped. The ball moved from the origin along the x-axis at a constant velocity. I think that by changing the 0.22 meter ball radius to the 0.011 meter that a mouse ball measures, it may have given me a more realistic appearance. Although the model position and experimental position are similar, the experimental values are slightly less. This may have to do with the table not being level or the fabric that covered the table increasing friction. In conclusion, I believe that my results support Newton's second law of motion.